This is part 2 in our series of lectures on section 3.3. In this lecture, we discuss the equivalence class theorem. So here's a statement of the equivalence class theorem. We start with a non-empty set A, and we let R be an equivalence relation on A. Then the following two results always hold. Any two equivalence classes of R are either identical or disjoint. If they have at least one element in common, then they must be identically the same. And secondly, every element of A is in one of the equivalence classes of R. So as a consequence of that, it follows that the set of distinct equivalence classes of R always gives us a partition of the underlying set A. Well, let's give a proof of the theorem. First, we'll prove number one, that any two equivalence classes of R are either disjoint or identical. So we begin by giving ourselves two elements of A, and we have to show that the equivalence class of X and the equivalence class of Y are either identical or they have nothing in common at all. Well, let's do a few simple calculations just to see, before we go into the details of the proof. It's really quite simple. So let me show you the idea. So imagine that the equivalence classes look sort of like this. So imagine this is the equivalence class of X, and say this is the equivalence class of Y. And we're assuming that there's something that's in the intersection. So there's something in there. Okay. So what does that mean? That means that X is related to Z, and it also means that Y is related to Z. Well, if Y is related to Z, this implies, I'll just copy the first one down again, X is related to Z, and the fact that Y is related to Z by symmetry means that Z is related to Y, and together these things imply that X is related to Y. And that's by transitivity. Now let's give ourselves any W that lies in the equivalence class of X. So that means what? That means that X is related to W, which by symmetry means that W is related to X. But if we combine that with the fact that we wrote here that X is related to Y, that we'll add that on here, X is related to Y, and so by transitivity that means W is related to Y, and by symmetry Y is related to W. And that means that W lies in the equivalence class of Y. So in fact, the picture isn't quite accurate. This W must be in the intersection. That's really what it's saying. It's in both of them. So that's the idea of the proof. We did that for an arbitrary W in the equivalence class of X, and we showed that it was also in the equivalence class of Y. That's the idea of the proof. And you notice in this proof we only make use of symmetry and transitivity. We haven't yet made use of a reflexivity of the equivalence relation, but we'll come to that later. So maybe you're in a position to finish off the proof yourself of that first part of the theorem. I'm going to go back and go over it with you, but why don't you see if you can finish it off? Try to show what I just did here informally, that if two equivalence classes have an element in common, then they have to be identical. I'll show you my proof in a moment. Okay, so I've returned to my proof of the result. We start with an X and Y in A, and we assume that there is something in common to their equivalence classes. So that means that there exists a set Z, an element Z of A, such that Z is in the equivalence class of X, and Z is also in the equivalence class of Y. By definition, that means that X is related to Z and Y is related to Z. By symmetry of R, it follows that Z is related to Y. I've used this one here. And so now we've got X is related to Z, z is related to y, so by transitivity, it follows that x is related to y. And then again, by symmetry, y is also related to x. So now we're going to prove this inclusion here. So we start by taking a w in here. Let w be in the equivalence class of x. That means x is related to w. Since R is symmetric, that means w is related to x. But we showed a few lines above that x is related to y. So we've got w related to x related to y, and therefore w must be related to y by transitivity. And by symmetry, again, y must be related to w. That's exactly what it means to say that w lies in the equivalence class of y. So we started by giving ourselves a w in the equivalence class of x, and we proved that it was in the equivalence class of y. That means that we have this inclusion. Similar proof will show the reverse inclusion. I won't include it because it's very similar to the above argument. And so we've proven the first part of the theorem. The two equivalence classes are identical if they have anything in common at all. Let's now turn to the second part, and that's really very simple, and that's going to make use of the reflexivity of the equivalence relation. Why don't you put your video on hold and see if you can write a proof of the fact that every element of A must lie in one of the equivalence classes of the relation R. Okay, so here's the proof. We have to show every element of A is in one of the equivalence classes of R. So give yourself an element of A. Since R is reflexive, X must be related to itself, and therefore X lies in the equivalence class X/R. That's all there is to it. And that completes the proof. In the next few lectures, we're going to look at some applications of this theorem.